Okay everyone, here's the second part of our chapter on kinetics. Now in this part we're going to learn about the rate law and how to calculate the orders of reactants. Okay, what is rate law? So the rate law we can write for any reaction. So for any general reaction occurring at a fixed temperature, if the temperature doesn't change, for any reaction we can write the rate law like this. Let's see, you have A plus B giving you C and D. Remember we earlier wrote individual rates like negative 1 over A delta A over delta T as such. Now this one, that rate is called the rate law. The way we write is we have a rate and then we have the rate constant. K is a rate constant which is specific for a given reaction at a given temperature. If the temperature doesn't change, for any reaction, one particular reaction, K is going to be a constant. Okay? And then A is the concentration of A and B is the concentration of B. And these M and N represent the orders of the reaction. And we will see in detail what does this order means. The exponents M and N are reaction orders and are determined by experiment. They are not the coefficients that we see over here. They have to be determined by running an experiment. We will see how we can find those values. The values of M and N are not necessarily related in any way to the coefficients A and B. So they are separate from these coefficient M and N. So they are called reaction orders and they are stoichiometric molar ratios. They are different. Okay. So reaction orders in a little bit more detail. A reaction has an individual order with respect to or in each reactant. For example, if a reaction A is our reactant, goes to products. Now we are going to relate this to the rate of the reaction. If the rate doubles when A concentration doubles, now let's say we are running a reaction and we put a certain amount of reactant and then you double it. When you double the concentration of A, if we can observe that the rate also doubles. We say that the rate depends on A first order with respect to concentration A, if it doubles. And the reaction is first order with respect to A. Now get it again, clear it again. If the rate doubles when A doubles, when you add the concentration, you double the concentration of A and then the rate doubles, we say it's first order with respect to A. If the rate quadruples, it increases 4 times when concentration A doubles. We say the rate depends on A raised to the power 2 and the reaction is second order with respect to A. Why do we call it second order? Because when you double the concentration A, rate quadruples. When the A doubles, rate also doubles. It is first order. If the rate quadruples when A doubles, it is second order with respect to A concentration of A. Okay. If the rate does not change, so we keep adding concentration of A, nothing happens. If the rate does not change when A doubles, the rate does not depend on concentration A. So it doesn't change. We say the reaction is zero order with respect to concentration A. So we're going to focus on zero order, first order and second order. Zero order means you double the concentration of A, nothing happened to the rate. First order, you double the concentration A, rate doubles. Second order, you double the concentration of A and then the rate quadruples. Okay, so that is what it means when we say a reactant is first order, second order or third order or zero order or a fraction. Okay. Here's an example of a plots of reactant concentration A versus time for first, second and zero order reactions. So this is in this axis Y-axis we have the concentration of A, and then the x-axis we have time. Now for a second order reaction, no, not for a second, zero order reaction, the plot would look like this, a straight line with the time. Okay, concentration. And then for a first order reaction, the curve looks like this. And this is for a second order reaction. When you plot concentration versus time. And if you do a plot based on the rate and the concentration of A. What did we say when the A doubles? What happened to the rate if it is a zero order reaction? Nothing happens. Rate doesn't change, right? So this is the concentration. So you increase the concentration, nothing happened to the rate. So the rate would stays the same. This axis is the rate. Zero order reaction, rate does not change by doubling the concentration of A. Now for a first order reaction, as the concentration doubles, rate doubles. Concentration doubles, rate doubles. So it is a linear relationship, first order reaction. So we can write rate equals K is the reactant constant, A is the reactant concentration raised to the power 1, which is a first order reaction. And this is how we represent a zero order reaction, A raised to the power 0. And for a second order reaction, what happened? When you double the concentration of A, rate quadruples. So it's an exponential increase. So the rate is written as rate equals K A raised to the power 2 for a second order reaction. Okay. Individual and overall reaction orders. Now we have a reaction here. For this reaction, 2 nitrogen monoxide plus 2 hydrogen molecules giving us nitrogen and water. Excuse me. And from experimental data, the rate law has found rate equals K is the rate constant. And when we are writing down the rate law, you will always see that we write it in terms of reactants. Our two reactants are nitrogen monoxide and hydrogen. NO, nitrogen monoxide and hydrogen. Okay. And so the rate is second order with respect to nitrogen monoxide. And hydrogen is first order. Okay. So notice here in this molar ratio, hydrogen is 2 moles. But we don't put 2 here because remember, orders and the coefficients are not related to each other. And this 2 right here is not because nitrogen monoxide had 2. It's because from the experimental data, it has found that reaction is second order with respect to nitrogen monoxide. Reaction second order with respect to nitrogen monoxide and first order with respect to hydrogen. Since it is 1, we normally don't write 1. But if it is 0th order, we normally don't write the concentration of hydrogen at all here. Okay. Now here 2 for nitrogen monoxide, first order for hydrogen. So it is third order overall. Individually second, first and third order overall. Okay. Note the reaction is first order with respect to hydrogen even though the coefficient for hydrogen in the balance equation is 2. Reaction orders must be determined from experimental data and cannot be deduced from the balanced equation. Okay. Now we are given some examples and let's see how to calculate the reaction orders. For each of the following reactions, use the given rate law to determine the reaction order with respect to each reactant and overall order. Now, this is the reaction 2 nitrogen monoxide plus oxygen giving you 2 nitrogen dioxide. Rate law is given to us as K is a rate constant with respect to the two reactants NO and oxygen. Okay, what is the order with respect to nitrogen monoxide? Rate law was given based on the experimental data. It is 2 here, so with respect to nitrogen monoxide it is second order. What about the oxygen? Since 1 is not written here, normally we don't write 1, so it is first order with respect to oxygen. So 2 plus 1, 3, so overall order would be third order. Okay, so the next one, we have acetaldehyde, CH3CHO plus CH4 methane. Acetaldehyde giving you methane, CH4 and carbon monoxide. Rate is given to us. Remember, always we write the rate in terms of the reactants. Rate constant K, reactant and order 3/2. So, if you look at the rate law, what is the order with respect to CH3CHO, which is 3/2, 3/2. Okay, and overall order also 3/2. So, the next one we have hydrogen peroxide H2O2, excuse me, plus 3 iodide plus 2H plus, giving us I3 minus 2 water as our products. Okay, and the rate law is given as rate equals K, rate constant. One of the reactants H2O2 and I minus given. And there is one more reactant H plus. It has not been written over here. What does that mean? Now let's see here H2O2. So with respect to H2O2, what is the order of the reaction? It is 1. Remember, the 1 is normally not written. So with respect to hydrogen peroxide, first order. What about the iodide? Excuse me. Remember, this 3 is the coefficient. Normally we don't write it. So it's 1 here, which is not written. That is also first order. So H plus, even though it is a reactant, it is not written here. Excuse me. Meaning it is 0 order with respect to hydrogen. That's why it's not written. So the overall order would be 1 plus 1, second order for the third reaction. Okay. Yeah. Excuse me. Reaction is first order in H2O2, first order in iodide, and second order overall. The reactant H plus does not appear in the rate law, so the reaction is 0 order in H plus. Okay. Okay. Now, we had seen the numbers Mn and we saw 0, 1, 2 for the reaction orders. But how can we determine the reaction orders? Let's look at the experimental procedure as to how we can determine these Mn values. So, we take a general reaction A plus 2B giving you C plus D. The rate law will have the form rate equals K, which is a rate constant, A and B. A raised to the power M, B raised to the power N. Since we do not know the rate orders, we're going to put them as M and N. Okay. So to determine the values of M and N, we run a series of experiments in which one reactant concentration changes while the other is kept constant. And we measure the effect on the initial rate in each case. Remember, we talk about there are 3 different rates that we normally measure. One is initial rate, average rate, and instantaneous rate. To find the rate law and M and N orders, we normally use initial rate. What we do is, if you have 2 reactants, we keep one of the reactants constant and then we change B. And then the next time we keep B concentration constant and changes A. And then we measure the initial rate. That's how we do the experiment. And these are some of the data that we obtain by running a reaction like that. So 4 experiment has been done, 1, 2, 3, 4. And these are the initial rates. Remember, as soon as the reactants mixed, you find the initial rate. We can find this from spectroscopic data. Okay. And we know the initial amounts that we put to perform the reaction. Now for the experiment 1, initially we put concentration A 2.5 into 10 to the negative 2. Concentration of B 3 into 10 to the negative 2. And you run a reaction and then you get the initial rate. And in the experiment 2, you perform another one. You add, now you double. You see here initially we have 2.50. Now you double the concentration of A, 5 into 10 to the negative 2. So for the second experiment, we keep concentration of B constant. You see, 1 and 2, we have the same concentrations B, but we double concentration of A and then get the rate data, initial rate. 3.5 is what we had found. And then you run another one, experiment 3. And this time you keep the concentration of A constant as 1, 2.50, 2.50. And we double the concentration, initial concentration of B. Initially we had 3. Now for experiment 3 we put 6 into 10 to the negative 2. You run another experiment and you monitor the initial rate, 3.5 into 10 to the negative 3. And you can do another one, the fourth one. Okay, for in the fourth one you double the concentration of this, you double the concentration, not A, you keep the concentration of A as experiment 2, 5 into 10 to the negative 2, 5 into 10 to the negative 2, and you double the concentration of B, 3 now becomes 6. Okay, now you can see that only first 3 would be sufficient for us to find out the orders, but additionally you can do experiment 4. Okay, so what experiment 4 is keeping the concentration of A constant. If you compare 2 and 3, concentration of A constant, that's correct, and you double the B from 2. Okay, now let's see with these data how can we find out the orders of the reaction. Concentration of B is kept constant for experiment 1 and 2. We saw that, while A is doubled, and then A is kept constant while B is doubled. Right? We saw that too. Now let's see how we can use this data to find out M and N. Now finding M, the order with respect to A. We compare experiments 1 and 2 where B is kept constant but A doubles. Remember the rate law? How do we write the rate law? Rate equals K constant A with order M and B order N. Now we have 4 different reactions. So for each and every one, if it is the first one, rate 1, rate constant going to be the same for all. So for the 1 and 1. And for the rate B, rate 2, if you write it K, and concentration A for the second trial, and concentration of B for the second trial. So likewise, for all 4 different reactions, we can write rate terms. And then we choose 2. So to find out M, order is with respect to A, we compare experiment 1 and 2. Because remember, in 1 and 2, we kept B constant. Now what we're going to do is we're going to use these 2 and we divide them. We can do rate 2 over rate 1. So that's what we have done over here, rate 2 over rate 1, because rate 2 has a higher data. So when you divide it, we can get whole numbers instead of decimals. Okay, so rate 2 over rate 1. So the K gets cancelled because it's under the same temperature. So the same rate constant K gets cancelled. And A2 is the concentration of A in the second trial. A1 is the concentration of A in the first trial, and their orders are going to be the same. Now for the B, remember the concentration of B was the same, right, for rate 1 and 2. Remember, concentration of B, initial B, so they get cancelled. So since it's a division, you can see concentration of B, they are the same, so we can cancel them. So we eliminate B term and K from our equation. And rate 2, remember the rate 2 from here? Initial rate 2 is 3.50, rate 1, 1.75. Concentration of A for the experiment 2, 5 into 10 to the negative 2. Concentration of A in experiment 1 2.5. So we use these for data. We divide 2 by 1 because 2 has a higher number, so we can get whole numbers. So you can see here rate 3.5 into 10 to the negative 3 over 1.75 into 10 to the negative 3, and concentration of A2 5 into 10 to the negative 2, and concentration of A1 2.5 into 10 to the negative 2. And then we do the calculation. 3.5 over 1.75, when you divide it, it would be 2. From this side also, 5 over 2.5, 2 raised to the power m. Okay. So I see a little typo here. Instead of n, it should be m. Okay. I mean, it's not multiplication. It is, that should be m. Is it m? It's n, right? M. So 2 from the left side, 2 from the right side. If you raise a number to this 1, that would be the same number. 2 raised to the 1, 2. Right? So m equals 1. So we found order with respect to A to A, right? Which is m equals 1. Now we can do the same thing to find out the order with respect to B. So we choose two reactions, excuse me, where we keep A constant and B changes. So you go back here and then you see we can use 1 and 3, right? So 1 and 3, 1 and 3 we keep A constant and we double B. So we can do experiment rate 3 over rate 1 because it's a bigger number. 3.5 over 1.75, 6 over 3, right? So let's do that. Finding n, the order with respect to B. We compare experiment 3 and 1 where A is kept constant but B doubles. So rate 3 over rate 1, K. Concentration of A in the third experiment over concentration of A in the first experiment. They are the same orders. And then the B. Concentration of B in the experiment 3, concentration of B in experiment 1. And their orders are N. So here we are going to find out B, and there is a typo. It says the B is being cancelled, but actually what needs to be cancelled is A. A is going to cancel because A has the same, right? So it's a typo that you see here, B crossed out. A cancels, not B. So this is going to cancel. We keep the B, okay? So B experiment 3 over B experiment 1 data. So B 3 over B1. So since both of these has the same coefficient, same order, we can even put a parenthesis right there. Okay. It's the same order. And we find the rate 3 from our table, 3.5 into 10 to the negative 3, 1.7. And then the reaction initial concentration for B, experiment 3, 6 into 10 to the negative 2. And then reaction 1, 3 into 10 to the negative 2. So 3.5 over 1.752, 6 over 3, 2. So n again has become 1. So the order with respect to A and B both are 1. Now that we found the order, so m equals 1, n equals 1. So remember we wrote the rate earlier, K, A, m, and B, n. Now with this experiment, we found what are the values for m and n, 1, 1. So now we know the rate low K, A. Normally we don't write 1, B. So this is the rate. Rate is first order with respect to A, first order with respect to B, and second order with respect to both of them. So the rate law is K, rate equals KAB. Okay. Here's another experiment. Initial rates for the reaction between oxygen and nitrogen monoxide, which is also going to be similar to what we did in the previous example. Now we're going to find out what are the orders M and N for this reaction. So this is the rate given as K, oxygen. You see here, this is going to be our reaction. So now you guys also should be able to write the rate K, not the K, rate equals K oxygen M and NO N. So we're going to find out M and N. So this is the same thing over here. Now tell me, to find out, what can we find out if you use experiment 1 and 2? Which order? Is it order with respect to nitrogen monoxide or oxygen? See, from 1 and 2, we keep NO constant. So we can find out the order with respect to oxygen when you use experiment 2 and 1. And which two can we use to find out the order with respect to nitrogen monoxide? We want concentration of nitrogen monoxide change, but oxygen kept constant. So we can use 1 and 3, right? 1 and 3, we keep oxygen concentration constant, but nitrogen monoxide concentration doubles. So by using 1 and 3, we can find out order with respect to nitrogen monoxide. Now you got the idea how we can find out orders. Okay. So with that in mind, this is what we're going to do. Finding M, the order with respect to oxygen. We compare experiment 1 and 2 where nitrogen monoxide is kept constant but oxygen doubles. So rate 2 over rate 1. Same, since the temperature doesn't change, K can be cancelled. Oxygen concentration in the second experiment over first experiment, their orders are M. And nitrogen monoxide we kept constant, so it can get cancelled. Right? This gets cancelled. So rate 2 data is 6.40 from the data table, and rate 1 3.21 from the data table, and oxygen concentration for the second experiment 2.2, first one 1.1. So now you do the math part. Okay, so 6.40 over 2.1, 1.99, 2.20 over 1.12. So 1.99 is almost like 2. So 2 equals 2 raised to the power m. So m equals 1. Anything raised to the power 1 is the same number, right? So m equals 1. So the reaction is first order with respect to oxygen. Okay. Similarly, we can use 1 and 3. Remember, we talk about 1 and 3 to find the order with respect to nitrogen monoxide, since we keep oxygen constant. So now we're going to use these two rate data, 12.48 over 3.21, 2.60 number over this number. Okay. Okay. Now before that, I want to tell you something else. So in these cases, it was obvious that the m value or the n was 1 in the previous calculations we did. So, but sometimes it might not be that obvious. So to find out the order, then you can use this logarithm term. The exponent is not easy to find by inspection. In those cases, we solve for m with an equation of the form a equals b raised to the power m. So we can write m equals log a over log b. So log 1.99, you get the log value, you get the log 2, you get the same number 0.993 like we got by inspection. So you can use this when we are having trouble looking or finding m right away. Okay. Confirms the reaction is first order with respect to oxygen. So reaction orders could be positive, integer, 0, negative, or fractions. So we do the same thing to find out the order for nitrogen monoxide. Rate 3 over rate 1, like I mentioned before. Nitrogen monoxide concentration in the reaction 3 over 1. And these are the rates: 12.8, 3.21. And from this side, we find the concentrations for NO, for 3 and the first reaction, third and the first, values taken from the table. Now this side, 12.8 over 3.21, we get 3.99, almost like 4. And from this side, we get 2. So 4 from this side equals 2 raised to the power n. So we need to find out n. And 2 times 2 is 4. So we can directly see n equals 2. But if you're having trouble seeing n equals 2, we can always use log term. N equals log A over log B. Log A is this value, 3.99, over log 2. When you do these calculations, you put the log values, you will get 2. So the reaction is second order with respect to nitrogen monoxide, and first order with respect to oxygen. So the rate law is rate equals K oxygen first order, nitrogen monoxide second order. So from the given experimental values, we were able to find out orders with respect to each individual reactant. Okay.